Back on, back on.
Very good. Alex is though.
Are we in? Alex, go down a little bit. You're strong. Okay, so, Alex, just move over here. Please, would you? Do you mind? Take your giant sandwich. You're going to say two Jesus. Okay, so, we're back. So, Amy, W1 tells us the secret to W2. It goes all the way around, and eventually, wait, look at the pictures later. Eventually, we get back to Wn. If you tell Wn, you just know. It's well known that if you tell Wn the secret, Wn is just going to turn around and tell W1, right? Say right.
Right.
Okay. So, here is what happens. We are going to construct two sets. We're going to construct set B. Set B is all the people who are friends with the snitch. So this is the set of all vertices. This is the set of all vertices such that Wn is an edge. Okay, so loosely speaking, B is all the people who are friends with the snitch. Okay, these are people who are friends with the snitch. People who are friends with the snitch. Okay. Then I'm going to create a new set. Alright, now this new set is much harder to understand. This set F is the set of all vertices such that Wi plus 1 W1 is an edge. Okay. Alright, and this goes back to the whole don't tell W1 I told you thing. Okay, so let's go through and look at the possible things that can happen, right? W1 tells W2 a secret. Okay, so let's say, this is just some scratch work over here. Let's say that W2, so let's say, do we want W2 to be friends with W, no, do we, okay, no. It's more like W3. So W2 tells W3, yo W3, I'm telling you the secret about W1, don't tell W1 I told you. Alright, now, W3, one response W3 can have is, I'm not even friends with W1. So wait, hold on. What?
Wait,
No, don't talk about that yet. Look, this is red. This is not a typo. Okay.
I think they're vertices.
What?
Wait, I thought they were vertices.
They are vertices. This is the set of vertices such that Wi plus 1 W1 is an edge. But I'm going to explain what that means now, right? Okay, so watch. So suppose so W1, everyone stay with me. Sage. Yep. W1 tells W2 a secret about herself. W2 tells W3. Okay. Now W3, upon being told, W2 tells W3, W2 tells W3, don't tell W1. W3 says, yo, I'm not even friends with W1, so I'm definitely not going to tell them. Well, if that's true, then who is happy? W2 is happy. Because W2 does not have to worry about W3 telling W1 that W2 told W3 the secret. Okay? Say okay. Okay, now, consider what happens next. Consider the fact that now W3 tells W4, hey, here's this secret about W1. W4 and W3 says, don't tell W1 that I told you. But now W4 is friends with W1. So now W3 is nervous. Okay? Why is W3 nervous? W3 is nervous because the person that he told the secret to is friends with W1 and might report back. Okay, so does everyone see how there are two possible states you can be in upon telling your secret? You can either be calm or you can be nervous. You're calm if the person you told the secret to is not even friends with W1, so could not report back to them that you told the secret about them. Whereas if you tell the secret to someone who is friends with W1, then you're worried that W4 is going to tell them. Are you with me? That is this set F. This set F is the set of vertices for which wi plus 1, also known as the next person they tell, is friends with w1. Okay, are we good? Okay, so put like hours of effort into this proof. Okay, so, maybe not that, like 1 hour. Okay, so, good. Let's make a couple of obvious observations. Here, and now I'm going to erase this purple line for the moment, because we understand the idea. What can we say about Wn being in set B? True or false? What does it mean to be in set B? You're friends with the snitch. Is the snitch friends with himself?
No.
Dude, no, because this is a simple graph. No one's friends with themselves. Okay, what can I say about Wn being in F?
Oh wait, no, that's.
The question is Wn, is the next person that Wn tells in the cycle, which by the way is W1 himself, friends with W1? No, because W1 is not friends with himself because it's a simple graph. Okay, so this says something interesting. It says that Wn is not in either of these. Okay, that's all it says for the moment. Okay, good. Alright. Furthermore, now, so here's what we know. Sage, we know there's at least one vertex which is not in either of those. Okay, now the question is, could there be a vertex which is in both of those sets? So let's just put a question mark and say something like, could WK be in F and WK be in B? We'll Spanishify this. How do we do this? No, that looks wrong.
Like it's reflective.
Like that? Whoa. That feels weird too. Okay, could there be a particular person who is in B and F? Okay, let's talk about what that means. What we are imagining, temporarily imagining, is that there is a vertex WK which is friends with the snitch. Okay? So I'll draw an edge connecting WK to the snitch. And, what's up? Wait, hold on. So first, I'm wondering what it means for a particular vertex to be in both of these sets. I'm seeing if that's possible. Okay, well, suppose that WK is in set B. If WK is in set B, the meaning of being in set B is that you're friends with the snitch, yeah? Okay, so far that seems fine. But is it also the case that what does it mean for WK to be in set F? WK is in set F if he is nervous, right? That's what being in set F means. It means you're nervous. And why are you nervous? You're nervous because the person you told might tell the story back again. Alright, well the person we told was WK plus 1, right? So if WK is in set F, it means he's nervous. It means that WK plus 1 must be friends with W1. Okay, well is it possible for this vertex WK to be in F and B? In other words, is it possible for him to be friends with the snitch, and also the person he tells in the Hamiltonian cycle through G prime is friends with W1?
No, because then there's a Hamiltonian cycle that doesn't go through.
Yeah, this is not totally obvious, but says Ramya, if this is an accurate friendship picture, then we can bypass the W1, Wn edge and still get all the way around the circle. Because now what could happen is W1 could tell W2's secret, W3, W4, until we get to WK. And then when we get to WK, WK could tell the snitch. And then what's the snitch going to do? Turn around and tell all of his secrets backwards. And then we get to WK, and then we go to W1.
What if K and N is 1?
What's up?
Could those two actually be the same person, K plus 1 and N? Like,
Wait, I think that if
Wait,
What?
I don't think it matters. I don't think it's going to change this argument at all, right? Because if
No, because if they're the same person, then there's no
There's
other
no-
cycle.
Yeah.
wait, hold on. Let me just finish this first, real quick, because and then we'll talk about your thing. The idea here is that if WK, so my answer to this Spanish question is an emphatic no, because if this were true, then that would mean that WK was friends with WN and WK plus 1 was friends with W1. But if that's true, then there is a Hamiltonian cycle in G. Because what does that Hamiltonian cycle look like? It looks like W1, W2, W3, and then we sort of like unfold, right? Dot, dot, dot. And now when we get to WK, what does WK do? It tells WN, and then WN tells WN minus 1, and we go backwards until we get to dot, 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 WK plus 1, and then WK plus 1 tells W1.
Isn't W and minus 1
W what?
Isn't W and minus 1 both sides?
In both sides?
Both sets.
Both sets? No. Wait, what do you mean?
Oh,
Yeah,
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 and it's
It's connected.
Oh, who cares about who's in both? Yeah, there's going to be a bunch of people in both sets, maybe. But wait, does everyone see how this is? Does everyone see how this is a Hamiltonian cycle in G? Right?
But
The Hamiltonian cycle goes jump, boom.
Wait, Mr. Rose, the
Yep.
point of this is that there isn't anything in both sets, but Wn minus 1 is in both sets.
Oh, wait, no. So then I changed my mind. Wn minus 1 is not in both sets.
But it is in both sets.
I have like an idea.
Unless you
Wait,
explicitly
wait,
say
wait,
it's
wait.
not.
Wait, no. There can't be anything in both sets. Didn't I just show that?
Except
no,
for-
because you assume
Wait,
that
hold
you
on.
could go from WK to WN. But if WK is WN, oh sorry,
Wn minus 1.
if WK is WN minus 1, then that edges this anyway.
If WK is Wn minus 1, then WK plus 1 is...
Then you can't avoid that WN to WN. Because then WK plus 1 is the same as WN, right? So you still.
Okay, wait, hold on. So, hold on. I think I need a new picture for this because it's getting complicated. But what was supposed to be the conclusion here is that this is a contradiction with the fact that G has no Hamiltonian cycle. So this is a contradiction with the fact that G has no Hamiltonian cycle. And what I was supposed to conclude is that that the intersection of F and V is empty. Alright, so I think that this is right. So now let me try to actually engage with your questions. Yes?
So the as drawn is fine because you have a bunch of distinct W's, but I don't know why you have to have that many. Like why is you labeled WK and WK plus 1 in such a way that neither is WN.
Okay, so
Suppose WK plus 1.
you guys think that WN minus 1 is in both sets?
Yes.
Okay, so let's draw it out. W1, W2, W3, and then I'll just get straight to WN minus 1, and then here's WN, and then can I just do this?
Yeah.
Okay, so is WN minus 1 in set B? Yes, because friends with the snitch. Is WN minus 1 in, oh, I guess I need to maybe, I think there just is no, wait.
Like, if that edge isn't there in the first place, we're not going to be worried about
Wait,
it.
hold on. So WN minus 1 is friends with the snitch, true. And is it also true that the person he tells is friends with W1? Wait. Now I'm like worried. What's wrong with that? Oh, yes.
So the thing
Because-
is that like you still won't have the Hamiltonian path when you get rid of W and W1. So the whole point of this is saying that there is no other Hamiltonian path, right? Like the Hamiltonian path has to go through WN and no other won't work anywhere else, right? So if WK is not Wn minus 1, it means there is another Hamiltonian path, but if it is Wn minus 1, well, it's the same Hamiltonian path, so it doesn't matter.
Wait, this is the crucial edge that we need to complete the Hamiltonian cycle. Wait, I'm a little.
Oh.
So I think that's more of a like, if you didn't have, it looks like those are just like, you can buy, F intersection B should just equal Wn minus 1, and then you can just, or reconstruct them such that it's explicitly any element that is an F and B creates another Hamiltonian path. Does that make sense?
Wait,
So like F intersect B would
No,
like,
no,
the size
but
of
I
it is
think-
1, so
I
it's only
think-
one Hamiltonian path.
but now I'm confused because they really do think that there's supposed to be nothing that's in both of them.
Wait, but like, if
What's the problem?
WK plus 1 is Wn, then when you delete the edge between Wn and W1, then you're also deleting the edge between WK plus
Yeah.
1 and W1. We said that when we go back to G, we take off the edge between Wn and W1. But when we go back to G and WK plus 1 is Wn, we also have to take off the edge between WK plus 1 and W1.
I didn't. Can you say all that again slower?
So for Wn minus 1, if we take n minus 1 to be k, WK plus 1 is Wn.
Yes.
So when we go back to G and we remove the edge between Wn and W1,
Wait, slow. We go back to G and remove the edge between. Okay.
because n is k plus 1, we also remove the edge between WK plus 1 and W1.
Right. Yeah, but my argument hinges on the fact that these two sets are really actually distinct.
It just puts it into two cases, one case where you use your argument and the other case where you were like, okay.
Mr. Rose,
Yeah.
are these constructed from G or G prime?
These are constructed from G prime. Not more than just G prime. They're constructed from like the Hamiltonian cycle that exists in G
Wait,
prime.
there just can't be an edge between something, what?
Well, hold on. Let me just finish the proof, and then maybe you guys can tell me why. There might be another case, as you're mentioning, but that can be ignored, or that can be dealt with separately. But the end of the proof, because I still don't think the proof is like the end of the proof is obvious yet. If these two sets are distinct, then I can say another thing, which is that the size of B is just, what is B? It's all the people who are friends with W1. So the size of B is just the degree of W1. That's a fact. And it's also true that the size of F, well, what is F? F is all the people in the Hamiltonian cycle who tell someone who's friends with Wn. But since every point in the Hamiltonian cycle is used, this ends up just being all the people who are friends with Wn. So so B is all the people who are friends with wait, I think I screwed this up. B should be all the people who are friends with the snitch. F should be all the people who are friends with W1. Or it's the degree of W1. Wait, don't zone out. Stop. Just playing like Sudoku? That's like terrible. Okay, Amy, put your phone away.
Doing Latin squares.
Liar. So this is the size of the set B is all the friends of Wn. The size of the set F is all the friends of W1. But also it's true that that nothing can be in both of them, I think. So if nothing can be in both of them, then what happens when I add up the size of B plus the size of F? Well, the size of B plus the size of F, since there's no overlap, is just the size of,
Shouldn't it be just like,
Yeah, well, okay, again, I don't even think I need that. I can just say, what is the degree of W1 plus the degree of Wn? Well, the degree of W1 has to be at least, this is at least as much as n over 2. And the degree of Wn is also at least as much as n over 2. So when you add these up, you get the degree of W1 plus the degree of Wn is greater than or equal to n, right? In other words, they're in this, if you take all the things which are in set B and all the things which are in set F, then the size of that B union F set is equal to the degree of W1 plus the degree of Wn, which has to be greater than or equal to n. But now we have a contradiction because there is one thing which is not in B or F. Since there's one vertex which is not in B or F, then that says that the union of B and F has to be less than n. In other words, not every vertex can be in B or F, because no vertex can be in both of them, and there's at least one vertex which is in neither of them. So if there's one vertex which is in neither of them, and there are no vertices which are in both of them, then all of these guys plus all of these guys has to be less than the total number of vertices. But here, we use our assumption that everyone is friends with at least half the people to say that the sum of the degrees has to be greater than or equal to n, and this is a contradiction, showing that the existence of this graph G is impossible. Who generally gets it? There's another technicality that we have to sort through, which is what you guys are talking about. But if I can somehow show that there's nothing that's in both sets, yeah. So now Eob is going to handle the special case. Can you help me with this?
I'm very sure the only special case is n minus 1.
The only special case is n minus 1. Is it truly in B and F? I guess it is, right?
Yeah.
It is. But
when you use n minus 1 as k, then like if you see the Hamiltonian cycle that you drew for G, it goes what? W1, W2, W3, dot dot Wk, Wn, Wn minus 1, dot dot dot, Wk plus 1. But there is no like Wk plus 1 over there. I mean there is no edge from Wk plus 1 to back to W1. So that isn't a Hamiltonian cycle. Like that cycle doesn't exist anymore.
yeah, but what about this argument that shows that? I'm still lost. I don't get it. But don't I need to show that?
Like you'll get to your contradiction, I think.
How will I get to the contradiction? Oh, he doesn't know.
Isn't it like
Wait, the contradiction of like which part? Like which contradiction?
Is that
My overall contradiction is with the fact that these two sets together cannot include all the vertices. And so it's kind of a counting argument, right? You take all the things that are in B and all the things that are in F. Since there's one thing which is in neither and there's nothing which is in both, then when you add up all the vertices in these two sets, you get a number less than the total number of vertices. But since these are equal to the degrees, then that's the essence of the argument. So there is a vertex which is in both sets, and I feel like things break down a little bit. But maybe, so I guess we just need to treat this special case separately and show why that still leads to a contradiction.
If it's W, so if W n minus 1, it doesn't actually add anything.
Or is it just a case that Wn minus 1, maybe it's this simple. Maybe it's that Wn minus 1 is in B and F, but it's not actually to be included as part of one of the degrees, because it's a G thing. Yeah, that's it. Okay, watch. This is sort of annoying. Gossett just skips this because it's sort of a technicality regarding indices, but it's actually not exactly correct to say this. This is not quite true. In fact, we might say false. There is a vertex which is in both of these. It's W n minus 1. No, W n minus 1. But though Wn minus 1 does contribute to an element being in both of these, why is Wn minus 1 in set F? Wn minus 1 is in set F because Wi tells Wn, and Wn minus 1 is nervous, and W1 tells because Wn might tell W1. In fact, does. Okay, but then it's this inference which is the thing, right? It's not, therefore then it's not technically true that F is the degree of W1. Because in G, the original graph, Wn and W1 are not connected. Is someone with me? If one person's with me, I'm happy. So this is also not quite true.
Wait, so Mr.
F is the degree of W1 minus 1. There is in fact one thing which is in both, but the proof works out anyway. Yeah.
This goes back to where are these derived, because now you're saying that this is derived in G.
It was always derived in G.
I asked if it was in the
Yeah. Oh, that's wrong. Yeah, this is G. These come from G.
So with that being in G and minus 1 isn't part, doesn't contribute.
Yeah, now I understand this thing you were mumbling like 10 minutes ago.
So yeah, now they're distinct because n minus 1 doesn't count.
Why does n minus 1 not count?
Because it's just not true that.
Okay, so it was perfect all along.
Yeah.
Okay, good. All right, now I get it. Thank you, Yoni. So yeah, so basically, if you don't think about it too much, this argument was perfect. If you start to worry about the technicalities, what Yoni is saying, he figured this out already 10 minutes ago. He says that as is an edge means edge in G. And so what you're saying is Wn minus 1 is simply not in F because Wn, W1 is just not an edge. It is an edge in G prime, but it's not an edge in G. So therefore, Eob, are you satisfied? Wn minus 1 is not in F. And so this is true, and everything is perfect, and the argument works. Okay, good. Every time I think I'm an expert in something, I'm not yet. Let's go over a little bit of homework. We don't have an hour left in this class?
No.
Should we just move on? Do you want to go over the homework, or do you want to just move on to new
Let's
things?
move on. Let's move on.
How was the homework? Yo, what? It was hard? It was long? Okay, good. Let's move on, because I've also prepared, and we can probably do the rest of this. We can probably do the rest of this lesson in like half an hour. Then we'll just go over the homework in an informal style. Okay. Good.
Half an hour.
What?
You say half an hour, but we all know it's going to take us.
You're on to me.
Wow.
Why don't you just take some more from
But yeah, Yoni, you're totally correct about things. Wait, there's also a very important piece of paper which is missing.
No, like I
If it's not as good, it means there's another one.
like I was looking at
Yeah, of course it should be in G. Okay, good. I now, hey, done? Good. Okay, Andy, Guan, can you turn the camera? We're gonna go over here. And meanwhile, like someone's gonna erase the board. Yeah, Gabe, can you erase the board? Okay, good. All right, what I want to talk about now is what it means for a graph to be planar. Okay, so a graph is planar if it admits a planar embedding. All right, what is a planar embedding? A planar embedding is a way of drawing the graph in which none of the edges cross except if they have, if they meet at an actual vertex. Okay, so for example, take the following graph. Let the set of vertices be A, B, C, and D, and let the set of edges be, and I'll just write them out. A, B, A, D, A, C, B, C, B, D, and is that it? 1, 2, 3.
CD.
4, 5. 1, 2, 3, 4, 5. Yep. No CD. Okay. As we have carefully defined graph at the beginning of the unit, a graph is a set of vertices and a set of edges which are unordered pairs of vertices. Well, let's now draw this graph. Well, one way to draw it would be to go A, B, C, D. I put no thought into where I place those vertices with respect to each other, because I don't really care. Now I'm just going to draw the graph. Well, what are the edges of this graph? AB is an edge. You guys following this? AD is an edge. AC is an edge. BC is an edge. And BD is an edge. Well, this is a perfectly decent picture of this graph. This is called an embedding. An embedding is just a way of representing the graph in 2D. But I am slightly sad about this graph because it looks as if lines BC and AD cross, but in actuality they don't, right? So with a little bit more ingenuity, I can draw them so that they don't cross. Like what if I just put D up here? Then it's like pretty again, right? So now I'm going to redraw it. So that's A, B. This time I'm going to put D up here, and I'm going to put C down here. Well, now I have a line AB, I have a line AD, I have a line AC, BC, and BD. Well, now I'm slightly happier about this because it just like looks better and it looks prettier. In particular, none of the lines cross. And the only places where they touch each other, the various edges, is at a vertex that indeed is part of that edge. Okay, so if a graph admits, if it is possible to draw, so what we have are these two graphs are isomorphic, of course, because all that really matters are the edges. So we say that this graph is planar. A planar graph, loosely speaking, is a graph in which it is possible to draw the graph without any of the edges of the graph crossing. Follow? Say follow. Yo.
Do they have to be straight lines?
No.
So
No.
you could have
You could
the
go-
points in that place and just made it curvy, right?
Well, yeah, just like around. Yeah, that's fine. Yep.
Can any planar graph be represented in straight lines?
No. Yeah, the lines being straight is irrelevant. It's more like about cutting through the regions. It's all like topological, so it's sort of like, yeah, the straight line doesn't matter for straight.
But like, could you do it? I feel like you could. I don't know.
No, Yeb says no. Okay, Gabe says no too. Okay, Gabe and Yeb have been studying this for like a year. Okay, so the famous example of this is you have 3 houses and 3 utility companies. So you have house 1, looks like this. You have house 2, it looks like this. Let's like suppose this one has like, oh, they have a cute picture in the book. This one has like an antenna on top, and it has like a little window and no door. You just have to parachute in. This house has a door, and maybe it also